worksheet, and we didn't get to it. If you weren't here last Tuesday, I have a few copies. Raise your hand. Anyone else? So, last time we arrived at sort of a visual understanding of, for BCC and for FCC, where permanent deformation happens. So for BCC, deformation happens on planes like this one. In directions like okay, so slip directions are in the family 1, 1, 1. So that includes these 4 directions. And the slit planes are in the family 1, 1, 0, and that includes 1, 1, 0, 1, 0, 1, 0, 1, 1, 1 bar, 1, 0, 1 bar, 0, 1, and 0, 1 bar, 1. All right, for FCC, slip occurs on the 1, 1, 1 type planes. In the 1, 1, 0 directions. And the slip planes are in the family 1, 1, 1. Okay, so slip, we'll say permanent deformation occurs when the shear component of an applied stress is high enough to cause dislocations to move on slip planes in slip directions. So permanent deformation in BCC happens on those planes in those directions. FCC happens on those planes in those directions. Slip planes are those that are most widely spaced. And slip directions are those in which dislocations would move the shortest direction. So the planes that are most widely spaced, we said, those are the ones that are densest. Planes that are densest are furthest apart from one another. And the directions where deformation occurs are the directions where the atoms are just one diameter from one another, literally sort of touching, most dense. So that's from last time. Now, if you look at that handout, you'll see for one side, the column under planes has these planes. On the other side, the column under planes has these planes. For FCC, there's 4 planes, 3 directions for each plane. Also on that table. For BCC, there's 6 different planes, 2 directions for each plane. And what's true about every direction and every plane is that the dot product is 0. So, for example, for the 1, 1, 0 plane, 2 of these directions are on that plane. The 2 that are on this plane are the ones that have a dot product of 0. So that would be this one, -1 times 1 plus 1 times 1 plus 1 times 0 is 0. And this one. 1 times 1 plus 1 times -1 plus 1 times 0 is 0. Now you don't have to remember which plane and which direction that's on that chart, but I just want you to know why those are where they are. Any questions about that? Okay. So the application of this. Let's say I have a single crystal of some metal, and I'm applying a stress and tension. And that stress, let's say, is applied in the we'll say A, B, C direction. So somewhere in that crystal, depending on whether it's BCC or FCC, there will be a plane where the dislocation can move and allow deformation in the slit direction. So, do we have to say, I guess we kind of do. No, we don't yet. So let's say that that plane that's activated, the plane that where this deformation can occur, is that plane. So that's a slit plane. Let's say that's activated. And that slit plane, depending on if it's BCC or FCC, is going to be in the 111 or the 110 family. For now, I'm just going to say it's the XYZ plane. And the perpendicular to that plane that is XYZ direction by definition. The direction that's perpendicular to the plane has the same Miller indices. And let's say that deformation happens in that direction. And we'll give that direction indices U, V, W. Now I need to know what is the shear component of that applied stress on that plane in that direction. So I have to define a couple more things. The angle between the normal, and it kind of looks like it might be 90 degrees, but it wouldn't necessarily be. The angle between the slip plane normal and the applied stress. The angle between the applied stress and the slip plane normal is given a symbol phi. And the angle between the slip direction and the applied stress is lambda. Now, rather than have to regurgitate our trigonometry, we'll just use an equation assuming that you can go back to your notes from trigonometry and know where it comes from. But I know that the cosine of phi is equal to applied stress, okay. I'm going to try to use colors here so you see where the numbers are coming from. A times x, b times y, plus c times z, divided by a squared plus b squared plus c squared times x squared plus y squared plus z squared. We don't care what the degree value of phi is, turns out. We only really care about cosine phi. So we're going to solve for that. So using that as a pattern, can you come up with the cosine lambda equation? So the applied stress is still here. A plus B times something plus C times something. And A squared plus B squared plus C squared is still there. But now we're going to use the indices for the direction. So this is A times U plus B times V plus C times W. And those are values, those are integers. And then U squared plus V squared plus W squared. So, calculate cosine phi and cosine lambda on a So the 3, 2, 1 direction would be our ABC. The 1, 0, 1 is our plane. That's X, Y, Z. And 1 bar, 1 bar, that's our direction. Now, how do I know which is the direction and which is the plane? Jesus.
The brackets, it tells us.
So if I've got regular parentheses, that means plane, and square brackets means direction. Usually, it's given as plane direction in that order, but not always, usually. So 3, 2, 1 is our ABC. So I'm getting that cosine phi is equal to 4 over the square root of 14, square root of 2. Does that sound right? Are we getting something like that? You don't need to get it down to a decimal place. Or you can. And I have cosine lambda is equal to minus 3 plus 2 minus 1, negative 2 over the square root of 14 square root of 3.
Why is there a square root?
Did I get that wrong?
No, well, just why is there a square root?
Can you?
You know, I don't have my hearing aids in, I'm sorry.
Oh,
Why is there a square root if we're just?
Did I not put that in the equation? Well, that's why.
No.
oh. That kind of makes sense, I guess.
That would help.
Oh,
Now, there's this number that's called the Schmidt factor. And it's equal to cosine phi times cosine lambda. So in this case, it would be negative 8 over 14 square root 6. And the magnitude of that Schmidt factor should never be more than 0.5. Okay, so far so good? The resolved shear stress caused by an applied tensile stress, of X in the A, B, C direction. Resolved shear stress caused by the applied tensile stress X, that's a value of how many megapascals in the ABC direction on the 1 bar, 1 bar slip system. And I'm going to change this X to just be sigma sub 0. So it's consistent with sigma being stress. Shear stress has a symbol of tau. And usually there's a R for resolved. So the resolved shear stress caused by that applied stress of sigma 0 in the ABC direction on this plane and this direction is equal to the applied stress times cosine of phi times cosine of lambda. That's how we calculate that. How big is that resolved stress? And cosine phi times cosine lambda never exceeds the magnitude of 0.5 times sigma 0. That's not to say that we put 0.5 here and this is sigma 0 squared. This is just a value. All right? So, let's try calculate if the applied stress is 100 megapascals in the 201 direction. Okay, plane. We have the 111 bar plane, which has 3 directions on it, slip directions on it. So you could look at your table, or you could come up with 110 type directions that make the dot product equal to 0. I like to just do this, 110, 101, 011. I know those 3 are different because the 0 is in a different place. And now I see if I have to add a negative anywhere to make the, oops. That's right. To make the dot product 0. So far, so good. All right, I'm going to make a column where I calculate the cosine of phi. So it'll be the same for all these, because they're all the same plane. It will be applied stress, 1 times 1 plus 1. Oh wait, I'm looking at the wrong thing. 2, 0 times 1 plus 1 times negative 1 divided by the square root of 2 squared plus 0 squared plus 1 squared times the square root of 1 squared plus 1 squared plus negative 1 squared. So 2 plus 0 minus 1, so that's equal to 1 divided by the square root of 5 times the square root of 3. And these are all the same plane, so that'll be the same for all 3. So the next column I calculate is column cosine lambda. And I'm going to use each different, here I'm going to use this direction. So I've got 2 times -1 plus 0 times 1 plus 1 times 0 divided by the square root of 2 squared plus 0 squared plus 1 squared times the square root of -1 squared plus 1 squared plus 0 squared. That's equal to -2 of the square root of 5, square root of 2. The next direction, I've got 2 times 1 plus 0 times 1 plus -1 times, 1 times -1. 1 bar here, over square root of 5, square root of 2. Oh, shoot, wait, hold on. Am I doing this right? This is -1, 1, 0. This should be -1, 1, 0. I was looking at the plane. No, it's +1, +1. No, 0. And 1. Let's do this. So +1, 0, +1. Good. The denominators will always be the same. So this is 2 plus 1, 3. So the last 2 times 0 plus 0 times 1 plus 1 times 1. 2, 0, 1, 0, 1, 1. There we go. Okay. If I get a negative value for Schmidt factor, it means that my shear component is in compression, which isn't going to cause any deformation. So what I have to do is I have to go back to the direction and change its sign, which just means every negative you make positive, every positive you make negative. So this becomes one bar 0. All it means is that the direction had its point at one end, and we're going to put the point at the other end. One bar. Wait. Yeah, here. So this now becomes a positive. And this one becomes a negative. And that changes this to a positive 2. And that changes this to a positive 2. Oh, yeah, right. Okay? So if you end up with a Schmidt factor that's negative, it just means you have to change the direction, because your direction right now is causing compression, which won't cause deformation. And finally then, the resolved shear stress is 100 megapascals, that's the applied stress, times 2 over 5 root 6. Okay, so we're going to use the BCC side of your worksheet to do a whole all subsystems. Oh, I have them all in there. Okay. Two. The stress direction is 1 bar. Means that's, because if this is 0, then so is that, and that, that, that. And it doesn't really matter what cosine lambda is. So if the cosine of the angle between applied stress and a slip system on a certain plane is 0, what does that tell you about the orientation of the applied stress regarding as it applies to the plane? If the cosine is 0, what's the angle?
90 degrees.
90 degrees. So when the cosine, when the results, when the plane is perpendicular to the applied stress, there's no result stress. It's 0. Okay, I filled in some of those. Let's take a break. And when we come back, second says identify the primary and secondary slip systems. So let me just note that 100 the stress was increased when it got to 100 megapascals, this metal started to deform. Which means wherever the result stress was highest, it was high enough to cause deformation. So, and so the result shear stress is highest here and here. So those are primary slip systems, the ones that have the highest value of cosine P, cosine lambda. So I'm going to mark them with a P for primary. And the ones with the second highest resolve stress are the secondary systems. There's always more of those than there are primary.
That makes sense.
So the primary slip system, one of them is 101, 1 bar, 1 bar 1. And 0, 1 bar 1, 1, 1, 1. Okay, the critical result shear stress is the yield strength times the maximum cosine phi cosine lambda. And we're told permanent deformation begins at 100 megapascal. That's the same as saying is the yield strength. So critical resolve shear stress here is our highest resolve shear stress.
Professor, wouldn't it not be, like with the subscript Y, it would be the subscript 0 with the stress?
Say it again.
The stress, you have the subscript Y for like yield stress, but shouldn't it be subscript 0 for like?
Well, in this case, sigma 0 is sigma y. So the applied stress is the yield strength,
Okay, yep.
right? In this case. Now, what that means is, when any slip system gets to 41 megapascals, it will be activated. When any of these get to 41 megapascals, it's activated. When the primary slip systems are blocked, then the secondary slip systems have to reach a resolved shear stress of 41 megapascals. So in the answer to D, so this is B, and there's C. In answer to D, now the stress is unknown, but we know that the resolved shear stress critical is 41. We know that. So that should be equal to whatever the applied stress is, and it's going to be bigger than yield strength, times the value of cosine phi cosine lambda for secondaries. So now we need to find out, well, how big does the stress, applied stress have to be in order for this product to equal the critical value? So that new stress has to equal 41 megapascals divided by 4 over 6 root 6. And that's going to be a number bigger than 100. So I get 152 megapascals. Okay. Any questions? All right. So, think about the last 4 digits of your ID number. Okay? So, the last 4 digits is A, B, C, Okay, the applied stress is just take the first three. Not multiplied together, but just the first three. So if your ID, last four is 2101, be 210. If your last four are 10120, it's 12. Okay? And then as far as the direction, let's let it be the B, C, 0 direction. Some of you might have huge numbers and I don't want them all to be big. So if you had an idea that was 2101, last four, then your direction would be 100. No, that's no good. All right, we're going to have to make it a B, C, D. Okay? So, it's unlikely anybody will get the same numbers. Possible. I'm going to work an example with my 4. Do I remember it? Oh. 9240 is mine. As a model, and then if you can't print what's on Blackboard, then make your own sort of facsimile of it, but please make it neat so I can find stuff, okay? I was going to do something other than just a problem, but so in my case, applied stress my number is 2940 9246. My applied stress is 924 megapascals. And I'm told that that is where it starts to deform, so that's the yield strength. Stress, direction is 240 direction. I didn't tell you what, oh no, I didn't say FTC, okay. So, you can use your sheet or you can just copy the columns and, onto a piece of paper if you want to preserve your sheet.
Bless you.